According to National Electrical Code Article 310.15b16, for installations in hot, moist locations or where the ambient temperature exceeds 40 degrees Celsius, which is 104 degrees Fahrenheit, conductors must be deaerated to 80% of their allowable ampacity. The concern regarding the ambient temperature inside the building reaching 140 to 160 degrees Fahrenheit is valid. Using the NEC temperature correction factor of 80%, number 12 THHN conductors would have a deaerated ampacity of 15 amps times 0.80 equals 12 amps. Each high-pressure sodium fixture draws 2 amps. With 7 fixtures per circuit, the total load is 7 fixtures times 2 amps per fixture equals 14 amps. Based on the deaerated ampacity and the fixture load, number 12 conductors would not be sufficient. Number 10 conductors would be required to handle the load safely. 14 amps divided by 0.80 equals 17.5 amps, so we can round up to 18 amps required ampacity. Number 10 THHN conductor ampacity is 30 amps. The type of insulation and building materials can affect the ambient temperature inside the building. However, even considering the reflective properties of galvanized metal, it is unlikely that the temperature will be reduced below 120 degrees Fahrenheit during extreme heat conditions. Ultimately, the inspector has the authority to make code compliance determinations based on their observations and calculations. If the inspector believes that number 12 conductors are not sufficient for the conditions, compliance with their request to replace the wiring with number 10 conductors is required. In addition to the inspector's concerns, there may be other factors to consider, such as the heat dissipation of the fixtures and the ventilation system's effectiveness. To address these concerns, firstly, consider installing additional ventilation, which would help reduce the ambient temperature inside the building. Secondly, spacing fixtures further apart, which would reduce the heat concentration in any one area. And thirdly, using fans on or near the fixtures, which would help dissipate heat from the fixtures. When dealing with high ambient temperatures in electrical installations, it's crucial to consider the National Electrical Code requirements for conductor ampacity deaerating. The NEC provides tables and guidelines to ensure that conductors are sized appropriately to prevent overheating and potential fire hazards. Firstly, let's delve deeper into NEC Article 310.15b16, which addresses the ampacity correction factors for ambient temperatures. This section specifies that when conductors are installed in locations where the ambient temperature exceeds 30 degrees Celsius or 86 degrees Fahrenheit, correction factors must be applied to the conductor's ampacity rating. These correction factors are based on the conductor's insulation type and the ambient temperature. Secondly, understanding the NEC temperature correction tables is essential for accurate conductor sizing. The tables provide correction factors for various insulation types, such as THHN, THW, and XHHW, at different ambient temperatures. For example, if a conductor with THHN insulation is installed in an ambient temperature of 50 degrees Celsius, which is 122 degrees Fahrenheit, the correction factor might be 0.82. This means that the conductor's ampacity rating must be multiplied by 0.82 to determine its allowable ampacity in its specific environment. Thirdly, calculating the deaerated ampacity of a conductor involves multiplying its original ampacity rating by the appropriate correction factor. For instance, if a number 12 THHN conductor has an ampacity rating of 30 amps, and it's installed in an ambient temperature that requires a correction factor of 0.82, the deaerated ampacity would be 30 amps times 0.82, which equals 24.6 amps. This deaerated ampacity is the maximum current that the conductor can safely carry in that environment. Fourthly, it's important to consider the total load on the circuit when selecting the appropriate conductor size. The total load is the sum of the currents drawn by all the devices connected to the circuit. In the case of high-pressure sodium fixtures, each fixture draws a certain amount of current. Multiplying the number of fixtures by the current draw per fixture gives the total load on the circuit. Fifthly, comparing the total load on the circuit to the deaerated ampacity of the conductor is crucial for ensuring that the conductor is adequately sized. The deaerated ampacity must be greater than or equal to the total load in the circuit. If the derated ampacity is less than the total load, a larger conductor size must be selected to prevent overheating and potential fire hazards. Sixthly, selecting the appropriate conductor size involves referring to NEC Table 310.16, which provides ampacity ratings for various conductor sizes and insulation types. This table lists the allowable ampacities for conductors in different temperature ratings, such as 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. The appropriate temperature rating must be selected based on the terminations and equipment connected to the circuit. Seventhly, considering voltage drop is also important when sizing conductors, especially for long circuit runs. Voltage drop is the decrease in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Eighthly, calculating voltage drop involves using Ohm's law and the conductor's resistance per unit length. The voltage drop is equal to the current flowing through the conductor multiplied by its resistance. The conductor's resistance can be obtained from NEC Chapter 9, Table 8. Ninthly, correcting for voltage drop may require selecting a larger conductor size than what is required for ampacity alone. If the calculated voltage drop exceeds the recommended limits, a larger conductor size must be selected to reduce the resistance and minimize the voltage drop. Tenthly, it's important to consult with a qualified electrical engineer or inspector to ensure that all NEC requirements are met and that the electrical installation is safe and code compliant. Electrical codes and regulations can be complex, and it's essential to have expert guidance to ensure that the installation is performed correctly. In summary, sizing conductors for high-pressure sodium fixtures in hot environments requires careful consideration of NEC requirements for ampacity, derating, temperature correction factors, total load calculation, conductor selection, voltage drop calculation, and consultation with qualified professionals. By following these guidelines, it's possible to ensure that the electrical installation is safe, reliable, and code compliant. In addition to the NEC requirements, there are other factors to consider when installing high-pressure sodium fixtures in hot environments. Firstly, the type of fixture and its heat dissipation characteristics can affect the ambient temperature around the conductors. Some fixtures generate more heat than others, which can further increase the ambient temperature and require additional derating of the conductors. Secondly, the ventilation in the building can also play a significant role in reducing the ambient temperature. Adequate ventilation can help to dissipate heat and lower the ambient temperature, which can reduce the need for conductor derating. Thirdly, the location of the conductors within the building can also affect their temperature. Conductors installed in direct sunlight or near heat-generating equipment will experience higher temperatures than conductors installed in shaded areas or away from heat sources. Fourthly, the type of raceway or conduit used to enclose the conductors can also affect their temperature. Metal raceways can help to dissipate heat, while non-metallic raceways can insulate the conductors and increase their temperature. Fifthly, the grouping of conductors in a raceway or cable can also affect their ampacity. When multiple conductors are installed in close proximity, their heat dissipation is reduced, and their ampacity must be derated accordingly. Sixthly, the altitude of the installation can also affect the conductor's ampacity. At higher altitudes, the air is thinner, which reduces the conductor's ability to dissipate heat. Seventhly, the presence of corrosive or hazardous substances in the environment can also affect the conductor's insulation and ampacity. Conductors installed in corrosive or hazardous environments may require special insulation types or additional protection. Eighthly, the maintenance and inspection of the electrical installation are also crucial for ensuring its continued safety and reliability. Regular inspections can help to identify potential problems such as loose connections, damaged insulation, or overloaded circuits. Ninthly, the use of energy-efficient lighting technologies can also help to reduce the overall heat load in the building. Energy-efficient high-pressure sodium fixtures or LED fixtures can generate less heat than traditional fixtures, which can reduce the need for conductor derating. Tenthly, it's important to stay up to date with the latest NEC requirements and industry best practices for electrical installations. Electrical codes and regulations are constantly evolving, and it's essential to stay informed to ensure that the installation is safe and compliant. In conclusion, installing high-pressure sodium fixtures in hot environments requires a comprehensive approach that considers all relevant factors, including NEC requirements, fixture characteristics, ventilation, conductor location, raceway type, conductor grouping, altitude, environmental conditions, maintenance, energy efficiency, and industry best practices. By considering these factors, it's possible to ensure that the electrical installation is safe, reliable, and code compliant.